Hello. Today, let's talk about longitudinal vibrations in a rod. Um, well, what we have is a system which you've seen in another guise before. For instance, when you saw um, a spring attached in one end, if you look at the spring, is say this part of the spring, it can shrink a little bit, can become this part, it can expand further, it can expand even further. So just talking about a small part of the spring, but it's actually moving back and forth in a somewhat larger space like this. So this motion, you can see this is the vibration of that part, is actually in the same direction as what the tension will be in the spring. So tension will be in the spring in the same direction, and because they're in the same, along same line, we say it's a longitudinal vibration. It's a longitudinal vibration. You have a similar situation when you have a rod. Let's see if you look at a rod. Whether it's tied here and here or free at both ends. So if you have a rod, and if you look at an element of the rod, say you have placed the rod so that this is along the x-axis, and you're looking at point x and x plus delta x. Let's see, this area of cross section is A. If you're looking at this rod, well, this will move about in much like that. So say this is the equilibrium, and then at some instant t, this thing is over here, this thing was over here, but this line, if you try to trace that, is that line in the material. This line, if you trace it, maybe it's over here. So now what we are calling delta x here, this is that much. It could be smaller, just schematically I'm drawing what can happen. So we need to say at what's happening at x, what's happening at delta x. So we need a new variable. So this is kind of like if we had a string. In the string, if you look at, you had a string. In the string problem, you had x-axis this way. At some point x, it was here, and some point x plus delta x. So this was y, and this is y. Y at x plus delta x at t, and this was y x at t. So those are the values of y's. But here we can't have y. This is the displacement variable. We could have called this not just y, because this happens to be the y coordinate here. We could have used a different symbol to indicate we're looking at the displacement at point x. So here we use a symbol psi x of t instead of y. So it's kind of analogous to that. And so this value will be for the same variable psi, just like same variable y at x plus delta x t. So if you look at So if you compare this, this says, well, at x, at instant t, you can say the displacement or deformation of the material is this minus delta x. So what do you have? So we kind of define psi of x plus delta x minus psi of x. That tells us deformation of an element which is of size delta x. Okay, so if this is which we can denote by delta psi. If you study elasticity, you can say that this is actually delta x has used to be delta x, and now is delta x had changed by this much amount. So we will say strain at this point is the change which happened delta psi over how big it used to be, or d psi dx. We're going to use strain just a minute. Let's look at how much material. So when we are trying to write equation of motion, the vibration, what kind of equation this material here will obey in space and time, how it's varying over space and how it's varying in time. Well, we want to write F equals ma for the mass element in delta x. Well, how much is that? Let's call it delta m. Well, delta m is going to be proportional to delta x, and it's going to be area. So that's the volume of the material that's contained in here times the density. This will be the density. Well, displacement equals delta psi in time delta t. So the velocity will be delta psi over delta t, and that's d psi dt, and acceleration will be d square psi dt square. So mass times acceleration will be it's all x components, so it's going to be we have a mass written down there, so we have a delta x times a times rho, that's the mass, and d square psi dt square. So this mass times a, and we need to figure out to complete F equals ma, we need to figure out F on element delta x. Okay, so we want to figure out how much force there is. Well, let's look at that element again in isolation. So you have this is the element we're talking about, and this is the material, and this is the point x, and this is the point x plus delta x. So if I knew what force is pulling on this side and what force is pulling on this side, we could tell what the net force would be. So if they're equal, then there will be no net force, there will be no acceleration. but because there is acceleration, we expect them to be different. Let's call this F1 on here and F2 here. So how do I get this force? Well, this material had expanded, so it became a different size material, and it used to be delta x, now it is delta x plus delta psi. So we can appeal to elasticity, where if you expand in elasticity, you may have learned this, that if you have a rod or length L and expand by pulling on it, L plus delta L, then there is a stress on this material develops, and that stress can be said to be how much at each point, how much force over the area of cross section, and it's related to strain, which is the percentage change in the length. And we say stress equals to Young's modulus times the strain, and this is the Hooke's law. So we can apply this over here. Well, we know if you know strain, then just multiply y, get a stress, and once I get a stress, I can get the force. So let's see what the formula for stress will come out to be. The strain here is delta psi over delta x, which is same as d psi over dx in the infinitesimal limit. So stress is y d psi dx, and we can say this is you can say this psi is a function of x and t. So I will get different stress at x and at x plus delta. So let's call it sigma. So I will get a sigma x of t will be y, which is independent of x, d psi xt dx, and then I'll get a sigma x plus delta xt. It's a little bit different depending on what the psi value is, right? X plus delta xt over dx. Well, force at F1 will be related to this times the area, and force F2 related to this times the area. So what I want is F2, so F on delta M will be F2 minus F1, which is sigma at x plus delta x t minus sigma at x and t times area A. Well, you can see that this is, if I divide by delta x, it's going to just be d sigma over dx delta x A. Now I've got the d sigma, that's this function. We can write down here and get a y second derivative of psi over and then delta x A. So this is the force and this is the MA. So these two together we can write F equals MA for delta M looks like y d square psi dx square delta x A equals to delta x A rho d square psi dt square. Delta x cancel delta x, A cancel delta A. So let me write down d square psi dx square equals rho over y d square psi dt square, which is, you can see it is a classical wave equation with a v square formula looks like this, with the d square, and so v square is y over rho. So this will be the wave speed. So this is a classical wave equation. So to recap, a whether the inside points of a vibrating rod will obey a classical wave equation with speed given by this formula. So you have had practice solving this wave equation before with different boundary conditions, both sides fixed, one side free, another side fixed, or both sides free, and the solutions will look identical. So you can go study. These things are in the book, Vibrations and Waves, and it will be in section 4.5. Section 4.5. Okay, I'm going to stop here. If you have a question, leave a note at the bottom of this video. Bye.